I remember we've been talking about compound circuits, but compound circuits are just a mixture of series and parallel circuits. There is nothing else. Circuits are either series or they are parallel or they are combined together. But we treat them differently. We have to treat the series separate from the parallel. Remember, a series circuit means that the electrons are flowing through every part of the circuit. The electricity has no choice. It has to flow through every single resistor, and that means that the current is the same at every resistor. In this case, there's 3 resistors and a certain voltage pushing the electricity through. The parallel circuit is where the electrons have a choice. They have different paths to take, and you can see the way it's drawn here, these 3 resistors are actually parallel to one another. But they're both circuits. The electricity still needs to get from one end of the battery to the other, and it's being pushed by a certain voltage. Now, the way we like to solve these is to draw them in a line. So we like to break that battery in half and draw those resistors out in a line, still from one end of the battery to the other. And for a series circuit, remember, all you have to do is add up the resistance of each individual resistor. Okay, so we're looking for the total resistance that this circuit offers. Okay, and what we can do is we can just add them up for a series and find an equivalent resistor that the battery feels. The battery doesn't know there are 3 resistors hooked up. It just knows that it's pushing with a certain voltage and there is some resistance. And then we can use Ohm's law, because once we know the total voltage and the total resistance, we know V and R, we can solve for the total current in the system. It's the same process for a parallel circuit. We're going to break that battery in half and pull the circuit out into a line. And in this case, we like to draw little junctions wherever there is a choice where the electrons can go take different paths. It's nice, and it helps to keep track of things, especially in more complicated circuits, if we can label those junctions. But other than that, it's basically the same. We're going to want to analyze to figure out what the total resistance that battery feels. And for the parallel circuits, you don't just add the resistance, you add the reciprocals of the resistance, then you take the reciprocal of that and get it down to, just like with the series, 1 resistor. That is the equivalent of all the resistors in the circuit. And then, of course, we use Ohm's law to find the total current. And then we will move back up. We'll take for parallel, we'll take the total voltage in this system back up, because for parallel circuits, the voltage is the same everywhere. But for series circuits, the current. So you either get to take the current back up to the next step or the voltage back up to the previous step. Okay, so let's do an example here. This is a much more complicated circuit than you've seen so far, but remember, it's just series or parallel. That's all there's involved here. It's still the electricity trying to get from one end of the battery to the other, and sometimes it has different paths. In this case, it's a 12-volt battery, so 12 volts of pressure pushing the electrons through, and there are 9 different resistors. Some of them are series and some of them are parallel. We just have to solve them separately. But the first step is we like to take that we need to label the junctions. Wherever the electrons have a choice, wherever they come to a parallel part of the circuit, it's nice to label them. It helps keep track of things as you're analyzing the circuit. Okay? And this seems overly complicated, but things like computer chips in your phone or whatever would have billions of these little circuits on its chip. And all computers or phones really do is count how many electrons come through the circuit and come through different parts of the circuit. That's why these circuits it's so important to be able to analyze them in the modern world. So what we do is we like to take that battery, break it apart, and pull it into a line. And boy, as I look at that, those hands are kind of, I don't know, maybe the animation isn't so great. But you want to pull it into a linear thing. And now it's really easy to see what's series and what's parallel. Here we've got this first resistor, 1 ohm, and it's in series with resistor 2, 3, and 4, but they are in parallel with one another. And then you go to resistor 5, which is all by itself. Then you go to resistor 4, or 6, 7, and 8. And, well, first of all, 7 and 8 are in series with one another, and those two are in parallel with 6. And then you come to resistor 9, a 5 ohm resistor, as the electrons flow through the circuit. The thing is that all we can do is do things that are only parallel or only series. We can't combine a group of series and parallel things in one step. So what we need to do is redraw this, and we can take resistors 2, 3, and 4, and we can use the parallel rule, the reciprocal rule, and add them all up together because they are all parallel. And we can also add 7 and 8 together because they are in series with one another. There's nothing else involved in 7 and 8 but a series circuit. So we can redraw this. Resistor 1 is the same, 5 is the same, 9 are the same, and 6 is the same, but we can combine 2, 3, and 4 into a single resistor using the reciprocal rule. So that either 1 over 1 plus 1 over 1 plus 1 over 2, then take the reciprocal of that and get that that resistors 2, 3, and 4 are equivalent to a single 0.4 ohm resistor. And then we can use the series circuit rule equation and just add resistors 7 and 8 together. 2 and 2 makes a single 4 ohm resistor. It's no different to the battery. The battery is still feeling the same resistance. We've just combined them. Now you can do different things in the next step. You could combine resistor 1 with this conglomeration of 2, 3, 4, and 5 because they're all in series. But 6 and 7 and 8 are now parallel. You can't combine them. What I'm going to do is I'm going to do this in one step. I'm going to combine resistors 6 and this 7, 8 together into one. And those are parallel, so I'm going to use the reciprocal equation. So 1 over 3 plus 1 over 4, and then take the reciprocal of that and get 1.7 ohms. So now we've taken this original, fairly complicated series parallel compound circuit, and we've redrawn it and compressed the parallel and the series where we could. We got all the way down to this one circuit that is just series. And now, since everything is just series, we can add them all up into one equivalent resistor. We use the parallel rule, add them up, and get that it's 10.1 ohms. So there's absolutely no difference to the battery or to the circuit in this first big drawn complicated compound circuit or this last one where it's just one resistor. It's 12 volts of pressure pushing electricity through 10.1 ohms of resistance. We can use Ohm's law to solve for the total current and get that there's 1.2 amps of current passing through the circuit. Now your job is to use our two rules that for series circuits current is the same everywhere and for parallel circuits voltage is the same everywhere, to go back and analyze back up through so that you find the resistance, the voltage, and the current at every single resistor. Okay, so just to give you a head start here, we know that in this first circuit, the current is 1.2 amps. But this one was actually made up of these 5 in series, and we know that for series, current is the same. So 1.2 amps here means it's 1.2 amps at each one of these 5 resistors. Now you have the resistance and the current at each one of these 5. So you have I and R. You can solve for V.